Good afternoon, everyone. In the beginning of the class, let us see new announcements. Okay, the first new announcement is May 2nd, 2022. Class videos uploaded. Hello everyone, I have uploaded the class videos of May 2nd, 2022 to YouTube. Their URLs are this, and this. Best regards, Wei Zhen. Okay, the next new announcement is the handout of Chapter 3 has been updated. Version 20220504. Excuse me. Hello everyone. Excuse me. I have uploaded the latest version of the handout of Chapter 3 to the eCourse2 website. The location and the file name are eCourse2 website, multiple input, multiple output techniques for wireless communications, course content, handouts, Chapter 3, handout 20220504.pdf. Best regards, Wei Zhen. Okay, next let us see the progress of the last class. Okay, sorry. Okay, in the last class we have taught to handout of Chapter 3, page 53, problem 9, solution, the last line, unfinished. Okay, please open the handout and turn to page 53. Okay, and search for problem 9. Okay. So problem 9, what is an additive identity? Okay, I think I need to zoom out it. Okay. Okay, solution. In mathematics, the additive identity of a set that is equipped with the operation of addition is an element which, when added to any element x in the set, yields x. One of the most familiar additive identities is the number 0 from elementary mathematics. But additive identities occur in other mathematical structures where addition is defined, such as in groups and rings. Okay, let us see some elementary examples. The additive identity familiar from elementary mathematics is 0, denoted 0. For example, 5 plus 0 is equal to 5 and is equal to 0 plus 5. Okay. In the natural numbers n, if 0 is included, the integers z, the rational numbers q, the real numbers r, and the complex numbers c, the additive identity is 0. This says that for a number n belonging to any of these sets, okay, n plus 0 is equal to n and is equal to 0 plus n. Okay, formal definition. Let n be a group that is closed under the operation of addition, denoted plus. An additive identity for n, denoted E, is an element in n such that for any element n, small n in capital N, okay, E plus small n is equal to small n is equal to n plus E. Okay. So next, problem 10. What is a group? Okay, why do we need to know what is a group? Okay, because it appears in the solution to problem 9. Okay, here, groups. Okay. Okay, let us see what is a group. Solution. First, let us see the definition of a group. A group is a set G together with a binary operation on G, here denoted dot, that combines any two elements A and B to form an element of G, denoted A dot B, such that the following three requirements, known as group axioms, are satisfied. Okay, the first is the associativity. For all A, B, C in G, one has A dot B, okay, parenthesis dot C is equal to A dot parenthesis B dot C. Okay, that is, if you want to compute A dot B dot C, okay, then you can compute A dot B first and then dot C, or you can also compute B dot C first and then compute A dot B dot C. Okay, the result of the left hand side and the right hand side of this equation will be equal. Okay, the second is identity element. There exists an element E in G such that for every A in G, one has E dot A is equal to A and A dot E is equal to A. Such an element is unique. Okay, it can be proved. Okay, but we are not offering a math class. Okay, so we do not plan to provide the proof here. Okay, it is called the identity element of the group. Okay, third, inverse element. For each A in G, there exists an element B in G such that A dot B is equal to E and B dot A is equal to E, where E is the identity element. For each A, the element B is unique. It is called the inverse of A and is commonly denoted A to the power of negative 1. Okay, example. One of the more familiar groups is the set of integers. Z is equal to dots, negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, 4 dots together with addition. Okay, you can check that the integers with addition satisfy the above three group axioms. Okay, this is an easy exercise. Okay, problem 11. What is a ring? Okay, why do we need to know what is a ring? Okay, because ring appears in okay, appears here, okay, appears in the solution to problem 9. Okay, let us see what is a ring solution. First, let us see the definition. A ring is a set R equipped with two binary operations, plus addition and dot multiplication, satisfying the following three sets of axioms, called the ring axioms. Okay. First, R is a abelian group. Okay, what is a abelian group? We will introduce it later. Under addition, meaning that, okay, first, parenthesis A plus B plus C is equal to A plus parenthesis B plus C for all A, B, C in R. That is, plus is associative. Okay, so it means that if you want to compute A plus B plus C, you can compute A plus C first. A plus B first. Then compute A plus B parenthesis plus C. Okay. Or you can also compute B plus C first. Okay, and then compute A plus, okay, parenthesis B plus C. Okay. The result of the left hand side and the right hand side of this equation are equal to each other. Okay, second, A plus B is equal to B plus A for all A, B in R. That is, plus is commutative. Okay, third, there is an element 0 in R such that A plus 0 is equal to A for all A in R. That is, 0 is the additive identity. Fourth, for each A in R, there exists negative A in R such that A plus negative A is equal to 0. That is, negative A is the additive inverse of A. Second, R is a monoid. Okay, we will introduce what is a monoid, okay, later. Under multiplication, meaning that, okay, first, A dot B parenthesis dot C is equal to A dot parenthesis B dot C. Okay, this means that if you want to compute A dot B dot C, you can compute A dot B first and then dot C. Or you can also compute B dot C first. Okay, then compute A dot parenthesis B dot C for all A, B, C in R. Okay, that is, dot is associative. Okay, there is an element 1 in R such that A dot 1 is equal to A and 1 dot A is equal to A for all A in R. Okay, that is, 1 is the multiplicative identity. Okay, third, multiplication is distributive with respect to addition, meaning that, okay, first, A dot parenthesis B plus C is equal to parenthesis A dot B plus parenthesis A dot C. Okay, please note that we do not say, we did not say that the priority of the dot is higher than the priority of plus. Okay, so we need to add parentheses on A dot B and A dot C. Okay, for all A, B, C in R. Okay, this is the left distributivity. Okay, next, parenthesis b plus c dot a is equal to parenthesis b dot a plus parenthesis c dot a for all a, b, c in R. This is right distributivity. Okay, let us give an simple example. Let us give a simple example. The most familiar example of a ring is the set of all integers z, consisting of the numbers, okay, dots, -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5 dots. Okay, the axioms of a ring were elaborated as a generalization of familiar properties of addition and multiplication of integers. Okay, next let us look at problem 12. What is an abelian group? Okay, why do we need to know what is an abelian group? Okay, because it appears in the solution to problem 11. Okay, let us go to abelian group. Okay, solution. First, let us see the definition. An abelian group is a set A together with an operation dot that combines any two elements A and B, small a and small b of capital A, to form another element of capital A, denoted small a dot small b. The symbol dot is a general placeholder for a concretely given operation. To qualify as an abelian group, the set and operation A and dot must satisfy four requirements known as the abelian group axioms. Some authors include in the axioms some properties that belong to the definition of an operation, namely that the operation is defined for any ordered pair of elements of capital A, that the result is well defined, okay, and that the result belongs to A. Okay, the first one is the associativity. For all small a, b, and c in capital A, the equation parenthesis a dot b dot c is equal to a dot parenthesis b dot c holds. Okay, that is, if you want to compute a dot b dot c, you can compute a dot b first, then dot with c, or you can compute b dot c first, then compute a dot parenthesis b dot c. Okay, the result of the both sides of the equation are equal to each other. Okay, the second one is the identity element. There exists an element E in capital A such that for all elements small a in capital A, the equation small e dot small a is equal to small a dot small e is equal to small a holds. Okay, the third one is the inverse element. For each small a in capital A, there exists an element small b in capital A such that, Okay, small a dot small b is equal to small b dot small a is equal to small e, where small e is the identity element. Okay, the fourth one is the commutativity. For all small a, small b in capital A, small a dot b is equal to small b dot a. Okay. A group in which the group operation is not commutative is called a non-abelian group or non-commutative group. Okay. Let us see an example. Okay. For the integers and the operation addition plus, denoted z plus. Okay. The operation plus combines any two integers to form a third integer. Addition is associative. 0 is the additive identity. Every integer n has an additive inverse, negative n. Okay. And the addition operation is commutative, since n plus m is equal to m plus n for any two integers m and n. Okay, next let us see problem 13. What is a monoid? Okay, why do we need to know what is a monoid? Okay, because it appears. Okay, let me search. Okay, because a monoid appears in solution to problem 11. What is a ring? Okay, so let us go to monoid. Oh, sorry, I do not establish the link. Okay, I will fix this problem later. Okay, monoid. Okay, let us see problem 13. What is a monoid? Okay, first let us see the definition. Okay, a set S equipped with a binary operation S times S to S. Okay, here times means the Cartesian product, which we will introduce later. Which we will denote dot, is a monoid if it satisfies the following two axioms. Okay, the first one is associativity. For all A, B, and C in S, the equation A dot B parenthesis dot C is equal to A dot parenthesis B dot C. Okay, that is, if you want to compute A dot B dot C, then you can compute A dot B first, then dot with C. Or you can also compute B dot C first and compute A dot parenthesis B dot C. Okay. The both sides of this equation are equal to each other. Okay, holds. Okay, second is the identity element. There exists an element E in S such that for every element A in S, the equations E dot A is equal to A and A dot E is equal to A hold. Okay, in other words, a monoid is a semigroup. Okay, we will introduce what is a semigroup later, with an identity element. It can also be thought of as a magma. Okay, we will introduce what is a magma later, with associativity and identity. the identity element of a monoid is unique. Okay, this it is 25 minutes. Let us take a break.